In this video, we are going to learn how to use vector addition and subtraction to solve relative motion problems. When we talk about the relative motion, we are really looking at a situation from different points of view or frames of reference. In this example, we are looking at three references: the plane itself, the ground below, and the air the plane is flying through. These three frames of reference give us three key velocities. So we have the velocity of the plane relative to the ground, Vpg. This is the plane's velocity as seen by someone standing on the ground. And we also have the velocity of the air relative to the ground, Vag. The motion of the air is actually the wind. So we simply call this the wind velocity. So Vag is the wind velocity. And the third one is the velocity of the plane relative to the air, Vpa. So this is what pilot controls, representing the plane's speed and direction through the air. The problem states that the plane needs to fly directly north from its departure point to its destination. So when we say that the plane needs to fly directly from the departure to the destination, it describes the velocity of the plane relative to the ground. So we have a vector Vpg points directly north. We also know that a wind is blowing from southwest, meaning the air is moving towards the northeast. So the vector Vag points towards the northeast. Because this is a gentle wind, its speed is relatively smaller than the plane's speed. So when we draw the vector of the wind velocity, its length is relatively shorter. You can think of it like this. The plane is flying in a giant invisible air bubble. The air bubble moves with a velocity towards northeast and will take the plane to move together with it. If the pilot points the plane's nose directly north, it means the plane flies towards north through the air. Then the plane will drift away and it will never reach to the destination. So we need to figure out how the pilot should adjust the plane so it will stay on course. Intuitively, we think the pilot should turn the plane slightly towards the northeast. That's actually correct, and this will counteract the wind and allow the plane to fly from the departure point to destination. But let's try to use our vector operations, which can tell us the exact direction and speed. Now let's set up our equation. We want to solve the velocity of the plane relative to the air, which is Vpa. So we put it on the left side of our equation. Vpa equals to, what do we write on the right side? Remember when we set up a relative motion equation, we always have Vac, which means the velocity of object A relative to object C, equals to Vab plus Vbc. And you see in this equation, the common subscript B cancels out, and leaving the A and C in the resultant vector. In our case, we have P and A in the resultant vector, so the right side must be two vectors, where the first one should be Vp something, plus the second one should be V something A. So we know we should have P here and A here. And the blank should be something that in common between these two vectors. As we've mentioned that we have three references, the plane, air, and ground. Obviously, we are missing here is the ground. So we should put G in the blank. So we should have Vpg plus Vga, right? So now we set up our equation, which means the velocity of the plane relative to the air equals to the velocity of the plane relative to the ground plus the velocity of the ground relative to the air. Now we already have our vector for Vpg, but it seems like we don't have Vga. What we have is Vag. So what's the relationship between this Vga and Vag? Or what's the relationship between the velocity of the ground relative to the air versus the velocity of the air relative to the ground? Vga is actually equals to negative Vag. Okay? Graphically, we can draw it like this. They have the same lengths, but opposite direction. So this is Vga. The velocity of the air relative to the ground is the opposite of the velocity of ground relative to the air. What does this mean? If you are viewing the air from the ground point of view, you will see the air is moving this way. If you are staying in the air somehow and looking at the ground, you will see the ground is moving in the opposite direction, right? Now we can add the Vpg and Vga together. How do we add them? We first translate the second vector Vga here, because when we do the addition of the vectors, we draw the second vector from the tip of the first vector. This translation doesn't change anything. The two vectors are identical as long as they have the same lengths and points to the same direction. So this is also Vga. So the resultant vector Vpa is drawn from the starting point to the ending point. So this is Vpa, which is how the pilot should turn the plane's nose to counterbalance the wind. Okay? Or we say the velocity of the plane relative to the air. We can also use the vector subtraction. Let's rewrite our equation as Vpa equals to Vpg minus Vag, right? Because we know Vga is negative Vag. So now we have the vector subtraction Vpg minus Vag. Then we can determine the Vpa by using the subtraction of two vectors. To subtract two vectors, we draw those two vectors from the same starting point. So we just use the two vectors we draw originally, this one and this one. And you draw the resultant vector from the second vector's tip to the first vector's tip. So this is the second vector's tip to the first vector's tip. So this is Vpa. So you see these two vectors, they are identical, the same length, same direction, both pointing northwest. The only difference is their position. They are simply a translation of each other. The problem here is straightforward because it just asks for the direction. So we can immediately choose northwest as our answer because the vector Vpa is pointing northwest, right? Well, we could use the speed and the angles to find the exact numerical components of these vectors. That goes beyond what this question is asking. If you want to learn that, be sure to click the link above for another video.